Modern risk management assumes extreme volatility can be smoothed out and controlled. But under sudden stress, that illusion of stability rapidly fractures. Over the past 2 decades, highly sophisticated forecasting models have repeatedly failed to anticipate systemic global shocks. During the 2008 financial collapse, quantitative models used by the banking sector underestimated risk and helped crash the system. 2 years later, complex operational models failed to prevent the Deepwater Horizon oil rig disaster. In 2011, the Fukushima earthquake and subsequent tsunami severed global supply chains with a suddenness that supply network algorithms had not accounted for. The corporations involved had invested heavily in risk compliance. They deployed sprawling frameworks of rules and historical data, designed specifically to sound the alarm before disaster struck. The error lies in categorization.
Firms routinely treat complex strategic and external risks as if they are routine operational issues that can be solved with a rigid set of rules. Treating enterprise risk as a predictable compliance exercise creates a false sense of security, leaving organizations blind to catastrophic vulnerabilities. The core problem is mathematical. As researcher Nassim Taleb points out, attempting to predict completely novel events by analyzing historical data is statistically unsound. This chart shows the trap of standard deviation. Risk managers assume that probability and severity behave predictably, clustering neatly in the center of an average distribution. But socioeconomic and environmental randomness does not follow the structured rules found in statistics textbooks. In complex networks, disruptions regularly exceed 20 standard deviations, shattering the bell curve and forming a fat tail distribution. These extreme outliers, often called black swans, are statistically highly improbable, but they determine whether the firm survives or goes bankrupt. Trying to optimize an enterprise around the accurate prediction of these rare events is a guaranteed path to insolvency. The math simply does not support it. To survive complex environments, firms must stop trying to predict the probability of a disaster and instead mathematically model their structural ability to absorb its impact. This requires a complete reversal in how executives evaluate exposure. Enterprise survival depends on decoupling your actual vulnerability from your ability to forecast the future. Consider the strategic component fallacy. Leaders typically look at their procurement budgets and assume that their highest risk lies with the suppliers who command the largest amount of capital. Modern supply chain topologies expose the flaw in this thinking. They are densely interconnected grids, and critical risk is often buried in the least expensive nodes. Corporations know exactly where their expensive, high-profile components come from. They build buffer inventories and forge strategic partnerships to protect these massive nodes. Because of this preparation, if a high-cost supplier goes offline, the network successfully routes around the damage and production continues. The real fragility lies in commodity parts. A 50-cent valve or a basic O-ring is often sourced from a single, overlooked manufacturer. If that microscopic, low-spend node is taken out by a localized flood or a factory fire, the entire assembly line halts. In highly complex systems, a node's systemic vulnerability has virtually zero correlation with its procurement cost. To map this true vulnerability, researchers like David Simchi-Levy developed a superior mathematical framework known as time to recovery, or TTR. TTR is simply the exact duration required to restore a specific facility to full functionality after any disruption. The metric ignores the cause of the disruption. Whether the trigger is a labor strike or a hurricane, TTR only measures the resulting impact of the node going dark. This scatterplot maps the supplier network of the Ford Motor Company, measuring total spend on the x-axis against lost profits on the y-axis to map the financial impact of isolating specific nodes. The data revealed that approximately 61, the single node that causes the most financial damage, is assigned a 1.0, and all other nodes are indexed relative to it, instantly highlighting the true structural exposures. By modeling the financial penalty of a shutdown, the REI focuses resources on vulnerability, removing the need to predict the specific disaster. While physical supply chains can be modeled with rigid mathematics, broader strategic risks, like market shifts or geopolitical conflict, still demand subjective human forecasting. Executives must constantly interpret cascading streams of ambiguous data to make high-stakes judgment calls. However, untrained human judgment is highly susceptible to cognitive traps.
forecasters routinely fall victim to anchoring, confirmation bias, and the pressure of groupthink. These flaws can be corrected. The Good Judgment Project, led by researcher Philip Tetlock, proved that predictive accuracy can be systematically engineered. When executives are trained in Bayesian revision, the rigorous process of updating probability estimates strictly based on the arrival of new data, their forecasting accuracy improves by 14%. The structure of the forecasting team also matters. The most accurate groups enforce a strict protocol. They spend time diverging to explore alternative views, evaluating the data constructively, and only then converging onto a single prediction. Effective predictive judgment is not a matter of innate executive intuition. It is a measurable, trainable organizational capability. Even with precise modeling and calibrated judgment, one final misconception threatens corporate strategy: the belief that idle capacity is an inefficiency that destroys shareholder value. As Taleb points out, decades of hyper-optimization have stripped organizations of their spare parts, leveraging them to the breaking point. A structure designed with zero tolerance for slack becomes brittle. It cannot absorb a sudden, unseen stress without snapping. Biological systems solve this problem through heavy redundancy. We have 2 lungs and 2 kidneys precisely to survive unexpected trauma. True enterprise resilience requires the deliberate integration of strategic redundancy. That means maintaining idle capacities, paying for alternative suppliers, and holding unallocated cash reserves. Organizations must stop trying to predict the exact timing and nature of low-probability extreme events. Long-term survival demands abandoning the illusion of perfect predictability. Instead, companies must optimize for rapid recovery, build structural redundancy, and